All right, so we are going to move on to the next section that we covered today, 7.4, the fundamental theorem of calculus. So by going to the fundamental theorem of calculus, we need a new definition here. So before, when we did integrals, we only did the approximation here. So in order to be exact, we want to use what's called the fundamental theorem of calculus. There are multiple um, parts to it, but we're just going to use this one. Depending on where you look, this could be part one or it could be part two. Um, so I'll call this part one of the fundamental theorem of calculus. So given any integral from a to b of f of x dx, that means that we can find any antiderivative f of x. This line right here is going to mean evaluate. So we're going to evaluate our antiderivative at b, and we're going to subtract when we plug in a. So f of x, capital F of x is our antiderivative. And it's going to be any antiderivative. I know we've been talking about f of x plus c. We don't have to worry about the c anymore, because when we do this right-hand side, f of b minus f of a, our c's will cancel out every time. So you will no longer have c's. You're going to have just a number as your answer. A and b are called our lower and upper limits. A is our lower limit, b is our upper limit. In general, b is going to be greater than a. So our notation, the notation f of b minus f of a means to evaluate the antiderivative at b and then subtract the antiderivative evaluated at a. Since both f of b and f of a contain the constant of integration c, they will cancel each other out, thus eliminating c altogether. If you still leave a c in your answer will be wrong every single time when we are talking about using the fundamental theorem of calculus or a definite integral. Now, the integral from a to b of f of x dx, just like we defined it in section 7.3, it's going to be defined in the exact same way. The difference between last section and this section is that in this section, we are actually going to find the exact value. No more using approximations, no more three methods to get to our answer. It's going to be one single method the entire time, and it's going to be straightforward and ready to go in every single case. So the integral from a to b of f of x dx is defined to be the area of the region between the curve of f of x and the x-axis bounded by the vertical lines at a and b if f of x is greater than 0. If it's not greater than 0, then we may end up having to break our integral up into multiple integrals. We'll see some properties in just a second that will allow us to show how we can do that. So some of the properties that we can have, these are the main properties whenever we talk about integrals that will allow us to be able to do this. So the first one, the integral from a to a of f of x dx is equal to 0 always. Because you're plugging in the same value, f of a minus f of a will give us 0 every single time. The second one, the integral from a to b of k times f of x dx is equal to k times the integral from a to b of f of x dx for any constant k. So anytime that we have a number that's multiplied in front, the technical way would be to factor the number out and then integrate that piece. That sometimes will be too cumbersome. Just take our antiderivatives and leave that number in front. The third case, the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So anytime we got multiple terms, just like when we did our derivatives, we took them individually. Same thing for antiderivatives. We are going to integrate them individually in each of our cases. For the fourth one there, the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx for any c value contained in that interval a to b. So say you have, if you had the integral from 3 to 6, then we could break this apart to 3 to 5 union 5 to 6. So in that case, C would be 5, A is 3, B is 6. We could break this apart. For number 5 there, the integral from A to B of f of x dx would be equal to negative the integral from B to A of f of x dx. So we can switch our limits of integration as long as we put a negative out front, because basically what that's doing is instead of going left to right, that put us going right to left, so we have to make our negation on inside of there. So it says evaluate each definite integral here. So the integral from 0 to 6 of x squared minus 8x plus 17 dx is equal to x cubed over 3, because antiderivative of x squared, you add 1 to the exponent, divide by the new one, so x cubed over 3, minus 8x squared over 2, which is minus 4x squared, and then plus 17x. Now keep in mind, this is evaluated from 0 to 6, because this is an antiderivative. It's the first fundamental theorem that we've been talking about. Now, when we plug in 6, we get a value. When you plug in 0 in this case, everything has an x, so therefore it's going to be 0 whenever we plug in 0. However, keep in mind that whenever you do your value for 0, if you have natural logs, you have exponentials, e's, they may not always be 0, so you're going to have to check to make sure of that when you plug in 0. Best thing, always come over here and plug in 0 every single time. So when we plug 6 into our antiderivative, we get 6 cubed over 3 minus 4 times 6 squared plus 17 times 6. By using our calculator, we can show that that is equal to 30. So 3 examples that we could look at. The first one is the integral from -1 to 4 of x squared minus x dx. Then we could look at the integral from 0 to 3 of e to the x dx. And then the integral from 1 to e of 1 plus 2x minus 1 over x dx. We must assume x is greater than 0 in this case. So the next couple slides, we work these out. So the first one, when we take the antiderivative of x squared minus x, we get x cubed over 3 minus x squared over 2. We plug in 4 everywhere for x, 4 cubed over 3 minus 4 squared over 2. Now, the way I like to do these, I like to go ahead and put a minus in a big parentheses, so that way we know when we're subtracting when we plug that in. So -1 to the third over 3 minus a -1 all squared over 2. Doing some simplification of our exponents, we get 64 over 3 minus 16 over 2. Minus, simplifying inside that parentheses, we get minus 1/3 minus 1/2. Running that negative through everything, we get 64 over 3 minus 8 plus 1/3 plus 1/2. And if we simplify that down, we get to 85 over 6. In this case, we needed to plug in 4 and -1, so make sure that you always do that. Now, for our e function one, the integral from 0 to 3 of e to the x dx, well, we know that the derivative of e to the x is e to the x, so the integral of e to the x is e to the x. So when we plug in 3, we get e cubed. Subtract when we plug in 0, so e cubed minus e to the 0 is e cubed minus 1. Do not forget this piece of e to the 0. If you forget that e to the 0, your answer is going to be wrong every single time because an exponential raised to the 0 is 1, not 0. So keep that in mind. The last example that we had there was the integral from 1 to e of 1 plus 2x minus 1 over x dx. So by doing this, we end up with the integral of 1 is x, integral of 2x is x squared, integral of minus 1 over x is minus ln of x, evaluated from 1 to e. So plugging in e first, we get e plus e squared minus ln e. And then minus when we plug in 1, we get 1 plus 1 squared minus ln of 1. Keep in mind that ln and e are inverses, so ln and e cancel each other out. If you remember back to your rules from Math 112 for inverse functions. Ln of 1 is 0 by definition as well. So you end up with e plus e squared minus 1, then minus 1, minus 1, and then plus 0. So we don't need to write the plus 0. So simplifying, we get e plus e squared minus 3 as our final answer here. So keep in mind, we got different variations on different things we could see based off of what's given and everything. So we're going to look at this one more graphically to see what's going on before we can kind of show what's happening. So the integral from 1 to 2 of x squared dx, this is the area of the region between the graph of x squared and the x-axis from x equals 1 to x equals 2. And we have the graph of this on the next slide here. So there's our function of f of x equals x squared. We are only concerned in what's happening between 1 and 2. I don't care what happens over here and over here. I don't care. We are only focusing in on this shaded piece right here. It can do whatever it wants on the outside. We're only concerned with what's happening on that little inside piece there. So a nice example in terms of business would be the following. Suppose that Y is the profit per mile traveled in thousands of dollars and X is the number of miles traveled in thousands. We're told find the area underneath Y equals 1 over X and over the interval from 1 to 4, then interpret the significance of this area. So on the next slide here, we actually perform this integration. First thing we have to worry about is how do we set it up? So this is the integral from 1 to 4 of the function they gave us of 1 over x dx. The antiderivative of 1 over x is natural log of x. And then we're going to evaluate that from 1 to 4. So we're going to get ln 4 minus ln 1. ln 1 is 0, so we have ln 4 minus 0. If you brought up your calculator, you could see that ln of 4 is approximately 1.3863. Keep in mind that our previous slide told us this was in thousands of dollars. So this area represents a total profit of $1,386.30 when the miles traveled increased from 1,000 to 4,000 miles. So keep in terms of our problems, we have to be able to remember that even though it says from 1 to 4, we're not really going from 1 to 4 miles because that's not a lot of difference. We're actually going from 1,000 to 4,000 miles, but we can simplify by plugging in these values to show that what's actually happening there and everything. So we're told, for this example, find the area under the curve of f of x equals x squared minus 8 from x equals negative 1 to x equals 1. So the antiderivative of x squared is x cubed over 3. The antiderivative of negative 8 is negative 8x. So really what we have is 1 to the third over 3 minus 8 times 1 minus negative 1 to the third over 3 minus 8 times negative 1. So simplifying, we have 1/3 minus 8 minus our parentheses of negative 1/3 plus 8, or 1/3 minus 8 plus 1/3 minus 8, which is 2/3 minus 16, which is negative 46 over 3. Now, this is an area problem. It told us in the thing, so we got to key in on that key word. Since it says area, that this minus 46 over 3, we actually need to take the absolute value of it to be 46 over 3 as our final answer. What that really means is that x squared was not above 8 in this specific case. What this between negative 1 and 1. So what we have to do is, it's really 8 minus x squared would have given us the positive of that value. But that's little technicalities that we don't have to worry a lot about in this course. Just understand that if you get a negative when it says area, we want to make it positive. Now, for this problem, it's not asking us to work out this problem. It's just asking us to figure out and think about this theoretically, what's going on. So for example, consider the integral from negative 1 to 2 of negative x cubed plus 3x minus 1 dx. I don't even really care about what that is since they gave me the graph. We just want to predict the sign of the integral by using what you know about area. Now keep in mind, we're not finding the area in this problem, we're finding the integral. That means two different things. In this case, when it says what we know about area. So what we know about area, we're looking at this piece and this piece. These are both below the x-axis, which means they're going to be negative values. Those two together create a larger piece than this gray area above. Therefore, we should get a negative answer. So it's not asking us to find area, it's asking us to find the integral. By finding the integral, we're using our knowledge of area of shaded regions or area of a region to determine which one's bigger. So from the graph, it appears that there is a considerably more area below the x-axis than above. Therefore, we expect that the sign of the integral will be negative. Easiest way to find that out, let's compute the integral that they gave us. So let's mirror. Keep in mind, it's the integral, not area. Those are two totally different things. So the integral from negative 1 to 2 of negative x cubed plus 3x minus 1 dx. So we integrate each one, we get minus x to the fourth over 4 plus 3 over 2x squared minus x, evaluate from negative 1 to 2. So you get negative of 2 to the fourth over 4 plus 3 over 2 times 2 squared minus 2. That's when we plugged in 2. Now we're going to plug in negative 1. So subtracting negative of negative 1 to the fourth over 4 plus 3 over 2 times negative 1 all squared minus the negative 1. So 2 to the fourth over 4, 2 to the fourth is 16 divided by 4 is 4. So that's where the negative 4 comes from. 2 squared is 4. 4 times 3 halves is 6. And then minus 2. Negative 1 to the fourth is 1. The negative out front. And then the negative out gives us negative 1/4. Negative 1 squared is 1. So that's just times 3 halves. And then negative 1 is positive 1. Distributing that negative through there, well, negative 4 plus 6 minus 2 is 0. So then you end up with negative 1/4 plus 3 halves plus 1. So you would have ended up with 5 over 4 plus 4 over 4, which gives us the 9 over 4. The negative out front gives us 0 minus 9 over 4. Noticing that we get a negative value, which is what we predicted without even doing any of the math. So it's always good to look at our problem sometimes if you can see the graph of it and say, okay, by looking at this, I should get a negative, or I should get a positive, or I should get probably close to zero, something like that. So that's kind of what we want to make sure that we're doing every time whenever we're going to do this. If you got questions, feel free to shoot me an email and we will get them answered.